In this episode, we are looking at a family of software weaknesses that has shaped cybersecurity for decades because it reveals what can happen when a program handles more data than the space it prepared for. Overflow vulnerabilities occur when software stores, counts, copies, or processes data in a way that exceeds the safe limits the system expected, and that breakdown can cause corruption, crashes, unexpected behavior, or in more serious cases give an attacker a path to interfere with the program's normal control. For a brand new learner, the simplest mental picture is to imagine pouring water into a container that was never designed to hold that much. If the container fills past its edge, the extra water does not disappear politely. It spills into places it was never supposed to go, and software can behave in a very similar way when inputs, calculations, or stored values exceed safe boundaries. Once you understand that basic image, overflow vulnerabilities stop sounding mysterious and start sounding like what they really are: failures to respect limits and systems that depend on precise boundaries to function safely. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A good place to begin is with the idea of memory and storage inside a running program, because overflow problems usually make the most sense once you understand that software uses carefully allocated spaces for information. A program may reserve one area for a name, another for a message, another for a count, and another for instructions about what to do next. Those areas are not just abstract concepts. They are real places in the program's working environment, and the software has to keep track of how much room exists in each one. When a program receives more data than one of those places can safely hold, trouble begins because the extra content may push into nearby areas and change information the program depends on. For beginners, it helps to think of a crowded filing cabinet where documents are stuffed into one folder until they start crushing the labels and papers in neighboring folders. The damage is not limited to the original folder anymore. The overflow begins affecting the organization of everything around it. One of the most familiar forms of this problem is the buffer overflow, and that term appears often because it captures the basic pattern very clearly. A buffer is simply a temporary holding area for data, often used while a program receives input, prepares output, or processes content internally. If the program assumes the buffer is large enough without checking carefully, and more data arrives than that space was built to hold, the extra content can spill into adjacent memory. That may sound like a technical housekeeping issue, but it becomes a security problem because nearby memory may contain important program information rather than harmless empty space. If that surrounding information is changed, the application may crash, behave unpredictably, reveal data, or lose control over part of its own execution. The key lesson for a beginner is that a buffer overflow is not just a case of too much data being annoying. It is a case of too much data crossing a boundary and altering things the program never intended to expose or change. Another important kind of overflow involves numbers rather than text or visible data blocks, and this is where integer overflow becomes useful to understand. Programs often use numeric values to track counts, sizes, lengths, positions, and available space, and they do so within fixed numeric ranges. If a program expects a number to stay within one safe range, but it grows too large, becomes too small, or wraps around in an unexpected way, the software may miscalculate what it should allocate, what it should trust, or how much data it should copy. In simple terms, the program loses an accurate understanding of size and quantity, and that mistake can create dangerous downstream behavior. Imagine a shipping system that uses a label saying a box contains only 2 items when it actually contains 2,000. The storage and handling decisions based on that wrong number will probably be unsafe. In software, a similar miscalculation can create conditions where the program believes an operation is safe even though the real amount of data or the real boundary is far larger than it understands. This is why overflow vulnerabilities are really about trust and boundaries. Software must constantly trust its own assumptions about how big something is, how long something is, how many items are present, or how much room remains before a limit is reached. When those assumptions are wrong or never checked carefully, the program is making decisions on false information that can cause different kinds of harm depending on what the affected data represents. Sometimes the result is only a crash, which is still a security issue because it can interrupt service or create instability. In more serious cases, the corrupted area may influence how the program behaves next, what permissions it uses, what data it exposes, or which instructions it follows. For someone new to cybersecurity, this is a helpful mindset because it reframes overflow vulnerabilities as failures of safe bookkeeping and safe limits rather than as magic tricks. The attacker is not inventing something from nothing. The attacker is abusing the fact that the program trusted unsafe assumptions about boundaries. A big reason these vulnerabilities matter historically is that they have often allowed a weakness in ordinary data handling to become a much larger compromise of system behavior. If a program stores too much input in the wrong place, the harm is not always limited to damaged data. The overwritten area may influence internal decisions, control flow, or stored values the program uses to determine what happens next. That is why overflow problems have been so important in security education for many years. They show that simple input mistakes can lead to effects far beyond the original form field, message, or file that introduced the data. In beginner terms, it is like riding past the edge of a worksheet and accidentally changing the instructions printed in the margin rather than just ruining the answer space. Once that happens, the program may stop acting like itself and start behaving according to corrupted information instead of its intended design. It is also useful to understand that not all overflow vulnerabilities look dramatic right away. Some create immediate and obvious crashes because the application touches damaged memory and fails quickly. Others are much harder to notice because the corruption affects a value or control structure that changes behavior later, perhaps only under specific circumstances or after the program performs several more operations. That delay can make analysis much more difficult because the visible symptom may appear far away from the original mistake. A user might only notice that the program froze, returned strange data, or ended unexpectedly, while the real root cause was a boundary failure several steps earlier. This matters for vulnerability analysts because it shows why overflow weaknesses often require careful investigation rather than simple surface observation. The visible result may be random-looking instability, but underneath that instability is usually a very precise failure to limit data correctly at the moment it was accepted or processed. Another layer of the topic involves where the overflow happens inside the program's working environment. You may hear discussions of stack overflows and heap overflows, and while those terms sound very technical, the beginner lesson is simply that programs use different regions of memory for different purposes. One area may be used more for temporary function activity and short-lived control data, while another may be used for more flexible dynamic storage that grows and changes during execution. If an overflow corrupts one region, the effects may center on temporary control structures. If it corrupts another region, the effects may involve stored objects, pointers, or application data that lives longer and interacts differently with the rest of the program. The exact mechanics are advanced, but the important idea is that the location of the overflow shapes what can be damaged and how the resulting behavior appears. Defenders do not need to memorize every memory model detail to understand the key point. Where the spill happens influences what part of the software world gets contaminated. For a first-time learner, it is especially important to understand that overflow vulnerabilities are rarely caused by one evil input alone. The deeper cause is usually a design or coding decision that failed to respect the possibility of unusual size, unusual quantity, or unusual numeric values. A program may assume user input will always be short, assume a file header is truthful, assume a count fits into a safe range, or assume the source of data already performed validation earlier. Those assumptions create brittle software because attackers, and even accidental malformed input, do not respect the polite boundaries the programmer hoped for. This is why secure development puts so much emphasis on defensive thinking. The question is not whether normal users would enter a long value or whether ordinary business logic would create a huge number. The question is whether the program remains safe when input is larger, stranger, or more deceptive than expected. Overflow vulnerabilities appear when the answer to that question is no. One of the reasons overflow problems remain relevant is that they show the difference between software that merely works and software that behaves safely under stress. A program may function perfectly during normal testing when users provide expected inputs and systems remain within normal operating ranges. That same program may become unsafe the moment it receives a value longer than expected, a count beyond the intended limit, or a file with deliberately malformed size information. This tells students something important about cybersecurity in general. Many security failures occur not because software cannot perform its basic job, but because it performs that job safely only under friendly conditions. Attackers do not provide friendly conditions. They search for the edge cases, the unusual values, the boundary assumptions, and the places where software designers quietly assumed no one would ever push past the expected limit. Overflow vulnerabilities are therefore a classic example of why resilience matters as much as functionality in secure software design. When defenders think about the business impact of overflow vulnerabilities, they have to consider more than the worst-case technical possibility. Sometimes the most likely result is denial of service, where the application crashes or becomes unstable when it processes unsafe data. That alone can be serious if the affected service is customer-facing, operationally critical, or tied to safety or availability requirements. In other cases, the real concern is data corruption, where stored values or calculations are changed in ways that undermine trust in what the system reports or records. In the most severe circumstances, the overflow may affect execution behavior enough to create a path for unauthorized control or deeper compromise. The point is that the same general family of weaknesses can lead to different kinds of business harm depending on where it appears and what the software does. A vulnerability analyst, therefore, should not stop at naming the category. The analyst should ask what this specific overflow could realistically damage in this specific system. Defensive strategies against overflow vulnerabilities begin with the principle that software must never assume boundaries without checking them. That includes validating sizes before data is copied or stored, using safer programming practices that reduce direct memory handling mistakes, treating file and input length information with skepticism, and performing numeric calculations in ways that detect overflow conditions rather than ignoring them. Good design also means choosing libraries, languages, and runtime environments that provide stronger safeguards where appropriate, because some development approaches make these mistakes easier to prevent than others. This is not a promise that technology alone solves the problem, since even safer environments can be misused, but it does show that secure design choices can narrow the opportunity for dangerous overflow behavior. For new learners, the key lesson is that prevention comes from respecting limits everywhere the program handles size, count, and storage. Overflow vulnerabilities do not emerge because boundaries exist. They emerge because boundaries are not enforced carefully enough. Testing and analysis play an important role as well, because overflow problems are exactly the kind of weakness that normal happy path testing can miss. Security-focused review asks what happens when the program receives more than expected, when values wrap around unexpectedly, when a file claims one size but contains another, or when one part of the system trusts a number produced by another part without verifying it independently. Analysts may not always see the whole problem from a simple scan result, since overflow issues often show up through crashes, unstable behavior, unusual exceptions, or inconsistent processing rather than clear text labels in a report. That is why debugging, validation, and careful reproduction matter so much in this area. The team needs to know whether the problem is just a stability issue, whether it corrupts important logic, or whether it creates a more serious security path. Good overflow analysis is patient work because the symptom can look small while the underlying cause is deeply structural. It is also useful to connect overflow vulnerabilities to the broader idea of secure coding culture. These weaknesses often reflect habits of thought rather than only isolated mistakes. If a development team assumes internal values are always safe, treats size checks as optional, or optimizes for speed without considering edge cases, overflow issues become more likely to appear across many parts of the codebase. By contrast, teams that think defensively about untrusted data, unusual ranges, and strict boundary enforcement are far more likely to catch dangerous assumptions before they become exploitable weaknesses. This matters because security is not only about patching a single bug after discovery. It is also about building development habits that reduce whole categories of mistakes in future systems. Overflow vulnerabilities remain an important teaching topic precisely because they expose how dangerous careless assumptions about size and limits can be in software that otherwise seems to work normally. The most important perspective to carry forward is that overflow vulnerabilities teach defenders to take boundaries seriously. Software relies on precise expectations about storage, counting, and control, and once those expectations are violated, the resulting effects can spread well beyond the original data being processed. Whether the weakness appears in a text buffer, a numeric calculation, or another memory handling path, the core problem is the same. The program allowed more than it could safely contain or interpreted a value in a way that crossed safe limits. That is why these vulnerabilities are such a foundational concept in cybersecurity education. They demonstrate how a failure to enforce something as basic as size can lead to instability, data damage, service interruption, and in some cases loss of control over program behavior. For a beginner, that lesson is extremely valuable because it reveals how deeply security depends on disciplined handling of ordinary-looking data. The big takeaway is that overflow vulnerabilities are boundary failures in software, where data, counts, or calculations exceed the safe limits a program was prepared to handle. Buffer overflows show what happens when too much content spills past a storage area, while numeric overflows show how dangerous incorrect size and count calculations can become when the program loses track of reality. These weaknesses matter because software is built on precise internal structure, and once overflow corrupts that structure, the result may be crashes, corrupted data, unstable behavior, or more serious compromise, depending on what was damaged. Strong defenders therefore treat overflow vulnerabilities as more than old technical trivia. They see them as a lasting reminder that security often fails when systems trust unsafe assumptions about limits. Once you understand that clearly, you are much better prepared to recognize why careful boundary checking, defensive design, and thoughtful validation are such central parts of modern secure software practice.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.